Hello everyone. Today we will continue discussing our topics on synchronous machines. So let me just refresh your knowledge about what we have discussed in the previous session. So we started firstly from the construction of the synchronous machine. We said that we have stator and stator windings. We have rotor and rotor windings, and we agreed that stator windings are three phases shifted by 120 degrees. And on the rotor side, we have the field winding, which is connected to the DC supply to build up the machine flux. And we discussed that we have two shapes of rotor. We have the cylindrical type, and this is a small diameter rotor. And we have the salient pool, which is large diameter rotor. And we discussed the different applications of every machine. And we discussed also the excitation, and we refer to the brushless excitation. The brushless excitation is the most preferred one. And this is the schematic of the brushless excitation. We discussed this in the previous session. And here the more detail about the discussion. We discussed also what the meaning of synchronous speed of the generator and what is the AC induced volt. So also we discussed that how the flux of the synchronous machine is rotating flux, and we derived this relation, and we end up with that since it's a sinusoidal waveform, so this is nothing but a rotating vector, and we mentioned that no electrical machine is going to rotate smoothly without having rotating magnetic field. And why here the magnetic field is rotating again? Because we, according to the derivation, we have two parts of the electric field, of the magnetic field. The forward part, and the summation of the forward part is this relation, and the backward flux, the phase shift between every phase is 120 degrees. So the summation is going to be 0. So this means backward flux equals 0, and you will have only rotating forward flux on this machine. So the machine rotates smoothly or the flux is rotating smoothly in the air gap. So now, since we understood the concept of the rotating magnetic field, let's start now, guys, discussing the equivalent circuit of our machine in order to create a mathematical model. So starting from the concept of the operation again, so you know that we supply the DC field winding by DC current, and since with the machine rotation we would have induced volt across the machine, and this induced volt will provide the current flow if you have a connected load. Now we have also what's called armature reaction. If you remember, guys, in the DC machine we discussed what the meaning of the armature reaction. So you have already the field winding. So the field winding is going to affect or produce induced voltage on the armature. However, when you have a connected load here and the current is going to flow here, the armature winding itself will have flux due to the current moving in the windings, and this flux will oppose the effective flux which is coming from the field. So this is called the armature reaction on the field winding, so we call it armature reaction. So the summation of the total induced voltages due to both is going to be or the summation of the effect of the armature reaction is going to be considered like that. So we would have the EF air gap volt. This is the EF, or the induced or generated voltage, and the armature reaction is going to be considered inside the synchronous reactance. So the synchronous reaction actually has two components. A first component is the winding leakage reactance and the armature reaction reactance. So this is the summation now of the reactance of the motor or the machine, including also the armature reaction. So as a conclusion, we can say that our our equivalent circuit is going to be nothing but the induced volt or the generated volt. Then we have the synchronous reactance of the machine, which includes the armature reaction, and for sure, the windings of the machine itself will have the ohmic resistance. So we would have also RA. You know, guys, for any kind of inductance or any windings, you would have the equivalent series resistance of the winding itself. And you know, resistance is nothing but rho L divided A. So resistivity of the wire, length of the wire, divide the cross-section area of the wire. So this would give you the armature resistance. So the armature resistance, you can measure it using ohm meter across the winding of the machine. As you know, guys, we will discuss the three-phase machine. So this equivalent circuit here, guys, is a single line diagram, which means we have this for the three phases, phase A, phase B, and phase C. However, because we have three identical phases, so all of the time we will consider that we have one circuit, which is the single line diagram. Okay, so this is here single line diagram, or let's say single line equivalent circuit instead of diagram, because we don't have a lot of circuits, just our machine. So this is single line equivalent circuit. So as you can see, guys, the circuit is simple, just a source of electricity, which is the effect of the field, synchronous reactance, armature resistance, and then the terminal voltage of the machine. So the load is going to be connected here in case of generating mode. And again, guys, don't forget that we are discussing the machine as generator and motor, okay? But the application-wise, mostly used as generator for the time being. Synchronous motors, we still have some synchronous motors in our industry, but it's very little compared to the other type of motors like induction motor. I mean the field-based machine. However, we have permanent magnet synchronous motor. It's used a lot in industry, and even it's preferred over the induction motor due to the higher efficiency. Okay, and later on we will discuss why the efficiency of the synchronous machine is higher than the efficiency of the induction machine. So we can say that our equivalent impedance of the machine is ZS, where ZS is RA plus JXS. RA is the armature resistance, and XS is the synchronous reactance of the machine. The power flow of this machine, guys, is very simple. Let's see together the power flow in case of generating mode. So for generator, you know that the input power is mechanical power. So Pn is going to be the applied torque, which is the shaft torque, times omega m. And again, don't forget that all the machine speeds are constant, which is the synchronous speed. Okay, so you don't have like induction motor. Induction motor, we have many speeds, but here we have a fixed speed, which is the synchronous speed of the machine. And you know, omega is the synchronous speed in radian per second, and n is in RPM. So this is the same synchronous speed that we have. So the input power is nothing but the applied torque, the shaft torque, times omega m. You would have some stray losses, friction and windage loss, and core loss of the machine. And we discussed before in the DC machine what the meaning of every term of these terms, what the meaning of a stray loss, what the meaning of friction and windage loss, what the meaning of core loss. So the remaining power, guys, is going to be the air gap power, or the converted power that would go to be converted to electrical power. So here we would have some electrical losses. So we have I square R, which is the copper loss of the machine. And again, take care that this is a general definition of the copper loss. It's I square R. However, it doesn't mean this is the relation in our machine. So the relation, we have three-phase machine. the armature current, so this should be IA, and the armature resistance. So if you would like to write down the exact relation of the copper loss, we would say P copper equals 3, because we have three-phase machine, IA phase value square times armature resistance. So the total copper loss is going to be the copper loss, and the remaining power, guys, which is going to be the output power of the machine, is the difference between the input power and all losses, or we can calculate this as root 3 V line I line cosine theta, like any power definition. So you know this is a general definition for any electrical power. Root 3 V line I line times power factor or cosine theta. For sure, you can say also 3 times V phase I phase cosine theta. And don't forget that cosine theta, theta is theta V phase minus theta I phase. All the time, guys, the power factor angle is the difference between the voltage and current angles. Okay, so this is the definition of the output power of our machine. Definitely, like any other device, if you would like to calculate the efficiency, so you can say efficiency equals P out divides P input. Okay, so this is the power flow diagram of our synchronous machine. Now, let's describe this, guys, more in deep and see what is the mathematical model. So, you know, in DC machines, we had a mathematical derivation for the equivalent circuit. The same is here also for the synchronous machine. We would have the relation between the generated voltage and the output current of the machine and the output volt of the machine. But in DC motor, we had DC power, which means we don't use or we don't supply reactive power. No reactive power, you know, in DC electricity. But in AC, you know that we have steady state, we have inductance, we have capacitance, so we have reactive power. So since the machine is working as generator, let's think about the concept of generator for the time being. And when we start discussing the machine as a motor, we would discuss how the machine can work as or at different power factor. Okay, but now let's say we start with the generator right now. So let's say for generator is going to be just a supply. So it depends now on our load. If our load is resistance only, so this would be unity power factor. So this would make the machine working at unity power factor. If our load is inductive load, so this is going to deliver reactive power to the load. So this means the machine is delivering reactive power and working as lagging. Or if we have capacitive load, so the capacitive load would provide reactive power to the supply, so the machine is going to be leading. So it depends now on our load condition. So in the first case here, guys, this is the lagging power factor condition. But I would like to draw this diagram with you in a separate slide to show you how to draw the phasor diagram from scratch. So let me create a new slide. I'm going to do that freehand and compare that with our phasor diagram. So in order to draw or make any kind of drawing of phasor diagram, guys, you need to have the relation. So we said that the relation is according to the equivalent circuit we have of our synchronous machine. So this is our equivalent circuit. You have here the EF, you have the impedance of our machine, which is ZS, and by the end, our load is going to be connected here. So this is V terminal, and the current is going to be output from here. So if you would like to get the induced voltage relation, so I can say V terminal plus I times Z. So this is the equivalent circuit, and here is our relation. EF equals V terminal plus IA times RA plus IA times JXS. For the ZS, as we mentioned, it's RA plus JXS. Let's see now how to draw the phasor diagram. So I'm going to say this is our relation again. EF equals VT plus JIA times XS plus, or let's say, sorry, let me write down the resistance firstly. Plus IA times RA plus JIA times XS. So this is our mathematical model. Let's draw the phasor diagram. So first thing is, for any phasor diagram, you have to have a reference. So we are going to assume, guys, that V terminal is our reference all of the time. Reference means that volt V terminal is the absolute value of V terminal, and the angle is going to be 0. So this is the meaning of having reference. So the first step is to draw the V phase. So this is V terminal. By the way, guys, this equation is per phase. This equation is per phase. Per phase means this terminal volt is V phase, not V line, okay? And all other terms are phase components. So this is V terminal phase value. Let's now state the lagging power factor case. So I'm going to start with the lagging case. Lagging case means our load is going to be absorbing current lagging to this volt. So lagging, I'm going to draw the current vector on the diagram here. It's not going to be added, guys, to the diagram, because by the end, the phasor diagram is going to be the summation of voltages only. It cannot be current plus volt. You cannot add current to volt, correct? So I'm going to draw the current just as an indicator to the direction of the current. So it's not a part of the equation. So let me have it in a different color. So I'm going to say this is the armature current. And for sure, the angle here is phi, which is the power factor angle. Now, let's have that mean voltage current again. So now, when you draw the phasor diagram, guys, we just draw the terms of the equation. So we draw already V terminal. So we draw the first term. The second term is IA times RA. IA is a vector. RA is a scalar value. So the vector IA RA is going to be in the same direction of IA. So this is the direction of IA. So I'm expecting that the IA RA is going to be in the same direction with the same angle. When we draw a phasor diagram, we draw the first vector. So we can consider now that the end of the first vector is the start of the second vector. So I'm going to draw IARA from the end of VT. So again, IARA is a vector in the same direction of IA. So I'm going to say this is the vector IARA. So now I draw these two terms, term number 1, term number 2. Let's draw term number 3. So term number 3 is J, which means right angle, 90 degrees, times IAXS. Again, IA is a vector, XS is a scalar value, so I'm expecting that IAXS would be in the same direction of IA. However, we have here J. J means right angle of 90 degrees. So 90 degrees with the armature current direction, this means the JIAXS is going to be in this direction. So I can draw now a vector of JIAXS. This vector is 90 degrees from the new point after the vector of IA. So this now represents JIAXS. Someone can say, why did we draw the vector in this direction? Why is not in the opposite direction? So all of the time, guys, if you have any vector like that, draw the 90 degrees counterclockwise. So the positive is going to be counterclockwise. So this is plus J. Okay. If you would like to draw minus J, it would be in clockwise. So this is now JIAXS. Do we have more terms here? We don't have more terms. So this means we finish drawing the right-hand side of our equation. The left-hand side is the summation of the right-hand side terms. So summation of any kind of vectors, guys, we're going to start from the first point of the first vector to the last point of the last vector. So this means the vector EF would start from this point till the last point here. So this would be the vector EF. Sorry, guys, this is freehand, but you can draw that using your ruler. So it's better to draw the phasor diagram using your tools. It's not going to be two scales, but you have to consider the angles, which means this is right angle, so it has to be right angle. Okay, otherwise this would be incorrect. Okay, guys. So this is now the phasor diagram in case of lagging power factor. The angle here is called delta, and we refer to delta by power angle. Why it's power angle? We will see that in few slides. Okay, but let's assume that the name now of the angle delta is power angle. So delta is the angle of the induced volt. So by the end, this vector here, EF, is going to be a certain voltage magnitude, and the angle is going to be delta. So this is the lagging power factor case. Let's go back to see this compared to our vector diagram here. So as we mentioned, guys, this is IA, this is the angle delta, and here the induced volt, the angle of the induced volt is delta, which is the power angle, and this is IA times RA, and this is JIA times XS. So this is the first case, which is the lagging power factor case. Now, if we have unity power factor, so the unity power factor means the armature current is in phase with the machine volt. So as you can see here, this is the second case, unity power factor. The armature current is in phase with our machine. So this means, guys, if you draw the phasor diagram, so this is going to be V terminal. IARA is going to be in the same direction. So this is IARA, and this is here JIAXS. So again, it's right angle on the IA direction. And the summation is going to be the induced volt. If we have leading power factor case, so this is IA, and this is V terminal, and this is also the angle theta, the power factor angle. IARA is going to be in the same direction of IA. JIAXS is going to be perpendicular to the current direction, as you can see here, and EF is the induced volt here. So these are the three cases, or the three possible cases that you can have for a synchronous generator: lagging power factor, unity power factor, or leading power factor. Okay, we need to have some important notes from the three phasor diagrams here. First one is As you can see, guys, the common thing between the three phasor diagrams is the power angle delta is positive. So this is the first note. All cases, power angle is positive, and this is gonna be, guys, for generator. So the power angle delta is gonna be indication for the power flow. So I can say this is power flow indicator. If delta is positive, so the machine is gonna work as generator. If delta is negative, so the machine is gonna work as a motor. Later on, when we drive the phasor diagram of the synchronous motor, you will find that for all cases of synchronous motor power factor, the machine, that power angle delta is going to be negative. Okay, so this is a first note. A second thing here is for the induced voltage, if you compare the three vectors magnitude of the induced volt, you would find that in the power factor, in the lagging power factor case, E is the largest. In unity power factor, you can say it's in the middle between the two cases. And in the leading power factor, it's the smallest value. From that, since the induced volt is, as you remember, when we say induced volt, which is EF, we mentioned that EF is 4.44 times flux times speed, or N, times winding factor, and so on, times speed or frequency. Okay, so frequency is our machine speed, or depend on the machine speed, which is going to be constant. So we can say that EF is indication of flux. So if the flux is high, EF is going to be high. If the flux is small, the EF is going to be small. So since we have here three different cases for the excitation or for the EF, so we can relate that to the excitation. Excitation is the flux that we have in the different cases. So we can say that in lagging power factor, the excitation is over excitation. In unity power factor, let's take this as a reference, so we are going to call it normal excitation. And in case of leading power factor, this is going to be under excitation. So we have three different cases for excitation. Over excitation in case of lagging, normal excitation in case of unity power factor, and lag excitation and under excitation in case of leading power factor. Okay, so these are the three cases that we have from here. One more thing is normal excitation. What the meaning of normal excitation? So normal excitation means EF cosine delta equals VT plus IARA. So this is EF. If we, guys, let's see that here, and this is going to be clear in unity power factor. This is EF. If we say EF cosine delta, so this is going to be this vector, correct? And this vector is nothing but V plus IARA. So you can say that EF cosine delta equals VT times IARA. So you can relate the excitation to the value of EF cosine delta. If the excitation is greater than EF cosine delta, this would be over excitation. If the excitation is less than EF cosine delta, so this would be under excitation. Okay, so we can relate the excitation to the EF cosine delta magnitude. Okay, now let's start discussing one of the important definitions and operations we have in our power system. So the definition is synchronization. What is the synchronization and what is the infinite bus? You know, guys, in our grids, we have so many power plants. And in order to have a reliable grid, you have to connect all generators and all loads together on a single network. So this means all the electrical supply and loads are connected to a single network, and we call it electrical grid. Electrical grid. So electrical grid includes a lot of generators with different types of mechanical supply. So you could find hydro turbines, you could find thermal turbines, you could find nuclear turbines, you could find oil, gas, steam, every type of generators. So all of these generators will be connected firstly to a transformer. So the transformer, if you remember, guys, when we discussed the transformer is used after generation to step up the voltage to a certain voltage magnitude. Here on this network, it's 230 kilovolt. So this is the high volt of our network, 230 kilovolt. And then we will start transmitting this power to our loads. You know that generation, we have in electrical grids, we have three stages: generation stage, transmission stage, and distribution stage. So after transmission, for sure, you will have your distribution. So here, for instance, we have a transformer to 44 kilovolt, then a transformer to 4.16 kilovolt. So this would be now the end to the distribution here in this voltage magnitude, 4.16 kilovolt. So after the 4.16 kilovolt, you would have a full transformer, which is going to convert the volt to a three-phase 230 volt and single-phase 115. Okay, so this is going to be the domestic loads, for instance. And you would have some other voltage levels for the industrial loads like 600 volt or 480 volt. So these are the different types of voltage levels you may find. So for the time being, guys, this is called, or the bus bar that would be used to connect all of these generators is called infinite. It's called the grid. Okay, and we would have one main bus bar as infinite bus. So the infinite bus definition is constant voltage, constant frequency. So if we assume that one of the generators here is going to be the main generator of our grid, so we can consider that the grid, the bus of this generator is going to be the infinite bus. Okay, so we would have just one infinite bus, which is going to be the reference of all other network. So this is going to be the infinite bus. So the definition of the infinite bus is nothing but constant voltage, constant frequency. And we would assume that the voltage of the infinite bus is 1 per unit all of the time, which is the reference value. So per unit means the actual value divide the base value. Okay, so this is called per unit system. Actual value divide base value. So all the time, guys, that generates volt, since we generate the volt from any generator at the rated voltage magnitude, and the base value is the rated voltage magnitude, so this would be 1 per unit. 1 per unit. Okay. So the bus bar or the infinite bus would have all of the time a 1 per unit value of volt, and frequency is our grid frequency, which is 60 hertz. So this is the definition of the infinite bus. Now, what is the meaning of synchronous? So we discussed the infinite bus meaning now. What is the meaning of synchronization? You know, guys, in order to connect a generator to the grid or to the infinite bus, you should have or you should fulfill some conditions. What are these conditions? We have 4 conditions here, but let me show you or make the 4 conditions in just one condition in order to be easier to be understood. So I'm gonna draw one thing right here. Let me add one more slide here and simplify the meaning of synchronization to you. Assume that we have an AC supply. So this is our generator here. And I have a switch. And I would like to connect that to the infinite bus. Let's assume that I have a single phase. If the infinite bus supply is this sinusoidal wave, so I'm going to say this is V infinite. And for sure, it's repeating after that. Okay. So you have a certain peak value, which is V maximum. And you have frequency. So if this is during a certain period t, so this means f equals 1 divided t. So this is our waveform of the infinite bus. In order to connect this generator to the infinite bus, let's say our generator here in a different color. So this is the generator supply. So the volt here is V generator. And in generator, guys, we start the operation of the generator by rotating the machine, creating the flux, and generating the sinusoidal waveform. So in order to connect this switch S, in order to close this switch to connect generator to the infinite bus, you have to have identical sinusoidal wave. So the sine wave of our generator has to be identical to the infinite bus sinusoidal wave. Otherwise, if you have any difference between the instantaneous value of the generator and the infinite bus, this would create a problem or a short circuit. So we have to have the same instantaneous value in order to synchronize the generator to infinite bus. How can we do that? Or before of how can we do that, let's say, what is the measurable value that we can say we can achieve the synchronization? So the measurable values from the waveform here, guys, in order to have two identical waveforms, okay, and matching together from the beginning to the end, firstly, we can say that both of waveforms have to have the same RMS value of volt. So same VRMS. But this is not enough because it could have the same RMS, but there is a phase shift. We don't need a phase shift. We need to have the equal instantaneous value. So we can say in order to achieve the equal instantaneous value, we should have also the same period of time, which means the same frequency. So we can say same frequency value or same frequency. So let's use the word same all of the time. Same means the value of the synchronous machine and the infinite bus. So same volt, same frequency. Is there any other factor? Yes. Like for instance, can you imagine if we have the same volt and the same frequency, but the volt of the generator started a bit earlier or a bit later? So you would have a difference as well. So a bit earlier or a bit later means you have a phase shift. So this is the third condition now. We have the same shift. So the phase shift of both have to be the same. These are the three conditions that you can have for a single phase supply in order to synchronize between generator and infinite bus. In three-phase system, you know that we have three phases. So we need to have the three conditions on the three phases. And having the three conditions on the three phases means having the same RMS value, frequency, and shift for phase A of generator and infinite bus, phase B of generator and infinite bus, and phase C of generator and infinite bus. You can have the same values, but for three phases, if you have a different phase sequence, this will not be achieved, even if you have it for one of the phases. So for a three-phase system, so I'm going to add now for three-phase system, which is our system now. So we need a fourth condition, which is same phase sequence. Because, for instance, imagine that you have phase A of the generator achieving the three conditions with the phase A of the infinite bus. However, phase B of the generator is connected to phase C of the infinite bus. And phase C of the generator is connected to phase B. So this is called out of phase. So in order to connect now the three phases safely, or on another way, let's say to synchronize the three-phase generator with the three-phase infinite bus, you have to achieve the fourth condition, which is the same phase sequence. So we have now four conditions, guys. So our conditions, as we mentioned now, you have the same volt, the same frequency, the same phase sequence for the three phases, and the same phase shift for every phase. So these are the four conditions that you have to achieve in order to synchronize a generator to infinite bus. And this is a simple diagram for what we are doing in order to synchronize the generators to infinite bus. So again, guys, here we have the EA, little a, and capital A. As you can see, E little a and E capital A. So E little a is referring to, according to the definition here, capital A is referring to the infinite bus. Little letters are referring to the voltage coming from the machine. So this is a generator. And what will happen if you don't have the same magnitude? So assume that we have A with A, B with B, and C with C, so we have the same sequence. Assuming that all the vectors are rotating by the same frequency, so we have the same frequency, and we don't have phase shift between phase A of generator and the infinite bus here, so the phase shift is already achieved. But we only have now a difference in the voltage magnitude. So this is little a, which is the generator, and this is capital A, which is the infinite bus. So the difference now is E capital A little a. This is the voltage difference between generator and the infinite bus. In order to achieve the connection, you have to have this volt equal 0, which means generator and infinite bus having the same value. How can we detect that? Simply, guys, if you have any voltage difference between the generator and the infinite bus, you can detect that on synchronization lamps. So synchronizing lamps, you will have some lamps like that between the generator and infinite bus sides. If the lamp is light, if the lamp is on, this means you have a voltage drop. So you cannot connect. If the lamp is turned off, so this means you don't have voltage drop. So this means you achieve the four conditions and you can connect to the supply. So we can detect that using a synchronizing lamps, as you can see here in this figure. This operation, guys, is not very easy, and there is a device called Synchronous is doing that control on two systems. One is called speed governor, and one is called automatic voltage regulator. So these two systems are controlled by the Synchronous in order to provide the synchronization conditions to connect the generator to the infinite bus. Okay, nice. Here, this diagram show you guys the different conditions that are not achieved to make synchronization. For instance, this is the infinite bus here, and this is the generator. But even as you can see here, this is E generator of phase A, this is infinite bus of phase A. Here we have B and we have C. They are in the same sequence and in phase. But frequency here is not the same. So at a certain time, you would have a phase shift. Okay, at a certain time, you would have a phase shift. So this is going to be the case now. After few time, since you have different frequencies, so the vector speed is not the same here like here. Okay, so at a certain time, you would have a phase shift, and this would make a difference. Here, this condition is for the phase sequence along with a phase shift. So phase sequence along with a phase shift, because between generator A and infinite bus A vectors, you have a phase shift right here. So this is a case of voltage different sequence and a phase shift at the same time. And here you have only phase shift, so we have the same frequency, so both of vectors are rotating with the same speed, and there is no phase sequence difference. So this is A, this is B, and this is C, but you have a certain phase shift between both of phases, so you would have a volt all of the time. So these are the three other conditions, guys. Okay, so these are the conditions that you cannot achieve the synchronization. So after synchronization, guys, as you know, for any kind of machine, in order to control and operate the machine, you have to know the parameters of the machine. The main parameter that we need to identify in the synchronous machine is the synchronous reactance. Okay. So what is the synchronous reactance of a synchronous machine? Sorry, how to identify the synchronous reactance of the synchronous machine? So this is a test can be made using what's called open circuit and short circuit tests. I'm gonna quickly discuss this in our class today, and in the next session, we will solve some numerical examples on the parameters identification of the synchronous machine. Okay, let's firstly say the open circuit test. So for the open circuit test, this means we would supply our field winding by current and leave the generator terminals open circuit and change the value of field current from small value to the rated current, rated field current, and measure the corresponding value of the voltage across the machine in order to get the induced phase volt. Okay, so this is called the open circuit test. So let's read this together, guys. The synchronous machine is driven at the synchronous speed. So you have to make this test at the synchronous speed, because as we mentioned, guys, the excitation curve is going to be different at different frequencies or different speeds. So you have to make this test at synchronous speed and open the circuit. So in this case, V terminal is going to be the same as the induced volt. You don't have current, you don't have voltage drop across your windings. So in this case, the volt right here is going to be the same as the induced volt inside the machine. But again, we don't need the line to line, we need the line to neutral. However, sometimes in our test, we may not have access to the phase value. So you can have access sometimes only to the line to line value. So you may find some tests, you have the line to line values in the test, and you need to convert that to a phase value, okay, in case of Y connection. So you have to divide over root 3 in case of delta connection. So line and phase values are the same. The curve showing the variation of the induced volt with the field current is known as the open circuit characteristic. So the open circuit characteristic, guys, is nothing but the relation between the excitation volt and field current. Now, let me show you this curve here. So the open circuit characteristic, this is the open circuit characteristic. So the open circuit characteristic, as we mentioned, we change the value of IF and find the corresponding value of EF and then draw our characteristic. So this is the open circuit characteristic. One point of the open circuit characteristic, guys, is going to be the rated volt of our machine. So we are going to increase the volt not to the rated value, but higher than the rated value until having saturation. Okay, so how can you detect that? When you increase the current, you would find that the increase in the voltage is not that high. It's going to be like saturated. So the difference of voltage increase or the rate of voltage increase is going to be small. So if the rate of voltage increase is small, you know that you are reaching the saturation, and for sure you passed already the rated value of the machine. Okay, so this is called the open circuit characteristic. We have two other curves, guys, and we use these two other curves in our questions. We have what's called modified air gap line, and we have what's called air gap line. What are these two lines? The modified air gap line is nothing but the linear line that moving from the origin here at 0 and passing through the rated voltage value of the open circuit characteristic. So this is called the modified air gap line. So this is the modified. What is the air gap line? The air gap line is the tangent to the open circuit characteristic. So this is mathematically, but what is the physical meaning? So the air gap line means the flux if you don't have core saturation. You know that for any magnetic circuit, guys, the core has a capacity, which means if you increase the field current on the windings, you will not get the corresponding increase in voltage in the output or in the induced voltage. And this is the reason why we have saturation here. But can you imagine now if you replace the core by just air? So we have air core inductance. Okay, so in this case, you don't have any kind of saturation. So the relation between EF and IF is going to be linear relation. And this is going to be the tangent that you can see here. So this can be considered as ideal because all of the time, our synchronous machine will have cores. No way to have synchronous machine with air core. You have to have a magnetic core. Okay, you have to have magnetic core to carry the machine windings. So this is an ideal curve. This is an ideal curve called air gap line. And modified air gap line, we are going to say the modified air gap line is a linear relation, but this relation is intersect with the open circuit characteristic at this point. When we can use the lines, the modified air gap line, guys, will be used if the machine is connected to the infinite bus. So if the machine is connected to the infinite bus, we can consider that our relation is linear because the grid is strong enough. So this is the modified air gap line that can be used only in case of machine is connected to infinite bus. But the open circuit characteristic can be used if the machine is disconnected from the infinite bus. Okay, so we call this is in islanded mode. Islanded mean it's not connected to the infinite bus. The generator is working without being connected to the grid, just a generator connected to a specific load without any kind of connection to electrical grid. So this is called standalone or islanded mode operation of generators. Okay, so we can use the modified air gap line if the machine is connected to the infinite bus, and we can use the open circuit characteristic if the machine is not connected to infinite bus, or we call it standalone generator or islanded mode generator. Okay, nice. So this is the meaning of the different characteristics. So here the note after that, the line passing through the linear part of the open circuit characteristic is called the air gap line, and the excitation volt would have changed along with this line if there were no magnetic saturation effects in the machine, which is an ideal case. So this is the air gap line, okay? And the modified air gap line, as we mentioned, is going to be used for the connected to infinite bus generator. Regarding the short circuit test, we make a short circuit simply by making wires, connect the wires across the machine windings and adding an ammeter here, but for sure you cannot make this test at higher excitation value, otherwise the current is going to be infinity theoretically. So this would burn the machine. So how can we do that test? Start with current from 0 value, increase the field current until having the rated current here. So don't increase the current over the rated value of the armature current. Otherwise, the machine will be burned. So the short circuit test, the ammeter 3-phase are shorted. For sure, once you connect ammeters like that, guys, the ammeter internally is a short circuit, so this would short our machine. The field current IF is now varied, and the 3 armature currents are measured. The variation of the armature current with the field current is known as short circuit characteristic. Note that short circuit characteristic is a straight line. This is linear relation. This is due to the fact that under short circuit condition, the magnetic circuit does not saturate because the air gap flux remains at low level. Okay, this is all of the time, guys, in case of short circuit. So when we draw the short circuit characteristic, so this is another X here, this is the IA, and we draw the line. So we need just small value, don't need to reach to very high values. So we can make the value at the rated current, as you can see here. You can make it at lower values, no problem. If you would like to test at lower than the rated current, this is okay, because as you mentioned, as we mentioned, that the relation is linear. So whatever the value you have, it has to be at most rated value, but you can have lower values as well. This is no problem with that because you have linear characteristic. What I recommend for that test, you can just take 2-3 values because the accuracy of the measurements. So if you have like 2-3 values and try to make a linear relation or interpolation between the points in order to get the straight line of the short circuit characteristic. In the next session, guys, we'll discuss how can we use these 2 tests in order to identify the machine parameters. Thank you so much and see you in the next session.